Welcome back to class. Before we begin, I want to show you where you can go after class for some additional resources. So this is a class that to register with various continuing education authorities, we have to register in advance and get approval and stuff like that. But the battery market changes constantly, and I do find that I revise this program content with regular frequency. And so I have a website where I put updated course slides and course video that after class you're free to check out to get additional notes or content or clarity if you wanted to. For example, I was just thinking about battery costs last night and how battery pricing has begun to kind of change. So before we get started again, I want to do just a real like here and now. These are battery pricing quotes that I've been getting or that you can obtain readily through just standard product distribution chains. And so the slides from the presentation yesterday were actually from a project presentation a couple years back. Industrial flooded lead acid. Now the main thing is that the industrial manufacturer is getting more aggressive with their warranty. And so there's an industrial flooded lead acid that I use that is $200 a kilowatt hour. That's rated for 3,000 cycles at an 80% depth of discharge. And so if you take the cost per kilowatt hour, and that's like the upfront storage capacity, and you divide out how many kilowatt hours come out of it over its useful life, you get the cost per kilowatt hour up front, and then the kind of levelized cost of storage, how much it costs to use over its entire life. And so the like absolute cheapest, without tax credits or anything like that, but the absolute cheapest you can get, industrial flooded lead acid is about 8 cents, 8.5 cents a kilowatt hour. The Tesla Powerwall is kind of a tough one because you can't buy the Powerwall without buying the inverter. Whereas like on an industrial site, you would have the inverter be separate from the battery, perhaps. And so what I've done in my Tesla Powerwall estimate is I've taken their retail pricing. Now this does not, I'm not trying to give you a total project cost or total hardware cost in this. I'm trying to do an apples to apples comparison of raw battery cost versus one technology versus another. So I've taken the Tesla Powerwall retail price and subtracted out what you would spend on the 5 kilowatt inverter that comes with the Tesla Powerwall. So I've backed that out of the pricing to come up with a cost per kilowatt hour to the consumer of about $300 a kilowatt hour, which I think is in line with Tesla's hard costs are around $200. So and so these are kind of like residential sized projects, small commercial sized projects, although it doesn't get much cheaper, at least in the industrial flooded lead acid. It could potentially get cheaper with these other two. We talked about yesterday the difference in like entry level lithium ion and top shelf lithium ion. So what I wanted to do is pull up a different competitor's warranty. And this is a kind of a top shelf lithium iron phosphate manufacturer. And you look at all their warranty information and terms and conditions, What I'm really interested in is reading the warranty to get kind of a quantitative performance evaluation on this. And here we go. We have a 10,000 cycle rating at an 80% depth of discharge is kind of the warranty for it. And there's one thing I want to point out. We're going to use this 80% depth of discharge because we have one from our lead acid guy, and we got one. We don't really have it from the Tesla Powerwall, but anyway, now so that we're on the warranty page, what I wanted to point out is if you deep cycled your lithium ion battery not down to 80%, but to 90%, and just got a little bit more energy out of that battery per cycle, the number of cycles you get out of it substantially decreases. And if you use that full 100% depth of discharge, it decreases even further. And so, what we saw in a degradation of battery performance with lead acid that really starts around a 20-hour discharge rate and gets down to by the time you get below a 6-hour discharge rate, you've lost all the performance out of your battery. What we're seeing in the lithium ion spec sheets, that something similar occurs with lithium ion, that maybe you can go deeper into lithium ion, but still operating the battery at the very end of its range, or fully discharging the battery in a matter of minutes rather than hours. All these issues that have to deal with operating the battery at its very bottom of its range, these degradation and performance issues still apply to lithium ion as they do to lead acid. So, it's just that lithium ion's stronger, so you don't get into these issues until you're down at 90 to 100% of the battery depth of discharge rather than 65% or 25%, depending on where you're at in your lead acid quality. So I guess what I would say is, it is appropriate to view, different battery technologies on the same shelf, saying, why would you buy one or over the other? It's generally assumed that, hey, lithium iron phosphate, everyone is saying, that's the quality stuff. But the upfront cost is substantially more. You're going to be, compared to lead acid, you would need to budget, almost 4 times as much for the same amount of raw storage. So, depending on your application, like in living off grid, where you're going to have to buy a whole bunch of storage, doing it all with top shelf batteries is really going to limit who your clients are and how many people can afford to do it. Although it will give you a longer lasting battery. Tesla's cycles, if you broke out their kilowatt hour warranty and you kind of backed into an 80% at 3,500 cycles gives them their kilowatt hour warranty. If we back it in that way, it turns out that at this point in the industry, like, the price difference between lithium ion and lead acid is really not the issue. These are all, I'd say, pretty competitive with each other. Yes, lithium ion will cost a little bit more per cycle than lead acid, but you'll get rid of performance issues in your system that will always leave you guessing, would I be having these power quality issues had I not went with lithium ion rather than lead acid? And lithium iron phosphate compared to entry-level lithium ion does offer marginal cost savings if you can afford to pony up the upfront cost. But is it worth the having to come up with 2.5 times as much project capital to buy the battery? What Tesla is banking on is saying, we want to be the best quality entry level lithium ion, because we want a lot of people to be able to afford to buy our products. And so, lithium, flooded lead acid, potentially still plays a role in that, for base load generation, when you need a whole bunch of storage, it will come in at the lowest amount of project budget, and that can still be a real issue. But, basically, to summarize kind of some conclusions from yesterday, you would only consider lead acid at this point when doing a large amount of storage for a residential off-grid system where you're not rapidly discharging that battery. Anything else by this point, you're really looking at either do you want to spend your money on entry-level lithium-ion like Tesla or LG, or do you go with kind of more obscure brands that are offering better than lithium-ion technology? And what's kind of pushed me over the edge, I used to be a pretty big lead acid guy. I've talked about lead acid in a lot of my course content. Now I'm starting to phase it out, is because I can now get lithium, entry-level lithium-ion used for about $130 a kilowatt hour. So the used car discount on some of these batteries, and literally they're used electric vehicle batteries. The car gets wrecked, they take the battery out and sell it to a secondary market, is now substantially cheaper than lead acid, to the point where it's like, if you really are budget constrained and on the fence, and so are leaning towards lead acid, I would think you'd have to do some soul searching and weigh the decisions between new lead acid and used lithium ion. That actually gets into some interesting code issues. In international building code, they allow used electric vehicle batteries to be used as energy storage systems for buildings. In National Electric Code, it's if you read it literally, they don't allow it. So you'd have to, I don't think you could plan on a business model of using used lithium-ion batteries unless you do a lot of exterior buildings where you put the battery outside the building. Anyway, we're going to talk about that in a little bit. Let's see. And then the other thing, I just wanted to better illustrate the grid assist configuration, where you're taking the input from the grid and then going through the inverter. But whereas a bidirectional battery inverter can also backfeed the grid, this is just a one-way inverter where the inverter output is completely different than the input. There's no backflow. So we have a question. If you use used car lithium ion batteries, what do you do with regard to cooling? Air-conditioned battery room is the best for it. But if you're putting the system outside, you may not always have access to that air conditioning. You would want, some airflow in your battery box, or to shade the batteries. LG Chem and Tesla, for that matter, will allow you to put their batteries in a garage or in a shaded area. It's still not a good idea to put the batteries outside without some type of temperature regulation. But it turns out that also applies to lead acid as well. There's concerns. Lithium ion is more of a solid state battery than lead acid is, and so the concerns about, say, battery freezing are more of a lead acid concern. You can usually get away with these temperature issues through some mild temperature regulation, like maybe a little electric heat in a battery box to make sure the temperature inside the battery box doesn't stay above, 10 degrees Fahrenheit or so. And then on the cooling end, shade, air conditioning is better. I might be wrong in assuming that the temperature underneath a car chassis is going to be greater than inside a shaded battery room, but I would suspect not. All right, so let's talk about that battery room. For off-grid systems, it's good to have a source of backup power. So, if one inverter fails, can you power it with another source? Stackable inverters power the same source. So, one inverter goes wrong. Sometimes they require some pre-programming, sometimes not. Some inverter manufacturers now, like Midnight, are making hot swappable inverter banks so that you could swap out a failed component without taking the rest of the system down. There's in the solar, we're used to just dealing with like one inverter for the solar array and sticking it on the wall. But now you have to keep in mind you might have a solar array and a battery on their own inverters. Even if you don't, if you have a DC coupled, you're using charge controllers. Nonetheless, those charge controllers and inverters take up space. And so, in the solar industry, we might have this mindset of, we can just find the garage space or some space on the wall for this equipment. But it's good to keep in mind that, like, hey, when you're doing not just a solar array that can power a house, but the battery component as well that can store the energy for the house, that can take up twice as much space as a regular inverter on the wall. And so I think it starts to make sense to plan where this equipment is going to be located, preferably indoors. If it's a small room in the garage, can you get some air conditioning into that garage? I think about like a water closet with a water tank in it in years past. That's just simply not enough room to house the entire power station for the building. So how much space do we need to plan for? In this particular exercise, we were using a 20 kilowatt solar array to power one house, which I think is pretty, it's a well-sized array for sure. Some homes that are all electric will need more than that. Some energy efficient homes will need less. We went with 600 volt charge controllers that had 2 circuits each going up to the array for 8 circuits total. If we had instead gone with 150 volt charge controllers instead of 600 volt charge controllers, we would have needed, 4 times as many. We would have had 16 charge controllers instead of 4 charge controllers. And, granted, those charge controllers would be, smaller, but you still got to install them and run all the wires and conduit together. The batteries themselves take up a lot of space, and the problem The problem is you don't want too much space, too much distance between your battery and your inverter, especially with lower voltage batteries. So we're in this weird time in the industry where no one knows, where the battery voltage is going to end up. And so we have like, lead acid communities that or sometimes at 12 or 24 volts, and then usually you go up to 48 volts. We have to remember that a volt times an amp gives us a watt. And so if I have let's just call it a 10 kilowatt inverter, if I'm on 48 volts, I have half the amperage as if I'm on 24 volts. And amperage is primarily what drives the thickness of the power cable between the two. And so the problem is the lower voltage battery banks, if you're trying to draw the same amount of power out of it, your cable is going to have to be twice as thick. And so, people are trying to power, a golf cart off a 12 volt battery. How much power do you need to power, an entire house? At that point, lead acid, you can find lead acid batteries that are rated for that amp hours, and essentially, how you have to keep in the back of your head, is my industrial lead acid battery rated for the load? You have to take that load and divide it by 6. And if your lead acid battery bank can be fully drained in quicker than 6 hours, then no, the battery's not sized for the load. The worst case scenario is you're gonna waste a lot of energy as heat. The best case scenario, the worst case is you start burning up the terminals on your batteries. And so we reduce the thickness of this cable, and we reduce the resistance that's caused by the electrons moving across this cable by just keeping these battery cable links short and close together. And so that essentially says that the battery and the battery inverter have to be located, almost right next to each other. It's a little bit less of an issue when you don't have a 48 volt battery bank, but instead you have a 380 volt battery bank, like you can get into with lithium ion, or even greater. 380 volts seems to be where it comes out. And what that allows you to do is to put the lithium ion battery right in the inverter and have smaller, at least smaller cables rather than thicker with 48 volts. So, which is better? Is it better to get a 380 volt battery inverter, or is it better to get a 48 volt battery inverter? Now the answer is you can do both. Often 380 volt battery inverters are specifically geared towards lithium ion batteries. So that's probably where things are going to go. At the same time, 48 volt is what's well established. And so if you're doing like a commercial grid tie or a small battery and you're trying to back up a critical load, you're probably going to be getting a higher voltage battery and not run your whole system off of it. If you're trying to get into residential off-grid, there's probably more components out there geared towards 48 volt systems than other voltages. Now I guess we'll come back to it. Okay, so if you're designing, say, a battery bank to live off grid, you have to remember that this is not something you can make a mistake on. If you don't size it correctly and they run out of power, they're going to be more than your typical upset customer, because they're putting in a lot of faith in your ability to deliver this kind of system. So how do we make sure that the battery bank is appropriately sized? We started to talk about that yesterday. What I do is I take the month-to-month electric bill and I divide by the number of days in the month. And so that's just an average. There's going to be days where you use more than that and days where you use less than that. But I just assume my battery bank starts at a certain amount, and then every day I subtract based off which month it is, based off your 12-month electrical bill history. I just subtract that amount out of the battery bank every day. And in this case, I've paired it with an on-site solar array, and so I've taken my PV watts data. And remember, in PV watts, you go and do the system production, you can download the hourly production data. And so, for every hour of the day, I put in my average building consumption based off, how many I consumed at the end of the month, how many days are in the month, how many hours in the day. And then I go in and I add back my solar production to simulate, charging the battery. And then I think that graphing this chart and looking at the data is very useful. And I do this with commercial battery sizing as well as residential, because there's a right sizing for solar peaker plants that you want to get down to. You don't want too little battery that you can't effectively load level your peak loads. At the same time, you don't want much spare capacity that you're not going to use, because then you're overspending on your battery bank. This is for a residential off-grid home, and this is the beginning of January. And what we can see is okay, well, there are sunny days in January where the solar array is well sized enough to fully charge the home back up to the top. And then we go through a weather cycle where we still have demand from the grid, or from the home drawing off our battery, but the solar array is not strong enough. And then we get into another sunny day, and then some more clouds, and some more sun, and some more clouds. And so we see okay, well, this is potentially a problem area. But then we get into spring and fall, and we're in the clear. We got nice sunny days, low electrical consumption. We can see that in the spring and the fall, our consumption is less on an average day than it is in the wintertime, or than it is in the summertime, for that matter. And we also see that, hey, there's actually some summer days that are going to be as problematic as winter days. And, it's not that we're not getting sunlight in the summer days. It's just that, we would either have to add more solar or do run the generator to bring the battery back up to the top of its range. And so then you can take data like this and start planning, okay, well, in order to protect my battery so that, if it's a lithium ion battery, I don't want it to discharge more than 90%, because I now know that it will hurt my battery if I do that. You can either, if it's a grid-tied battery, that's easy. It's a programmable setting. Once it's discharged down to 90%, recharge it. No problem. If you don't have the grid option, you would connect the battery to a generator. And so when I'm doing, say, off-grid planning, I take this data and I can actually count, how many times a year I'm going to need to run that generator based on the average weather data that's being pulled in from PV watts. And so I'll actually look at the generator and the generator runtime, because the question is, is it worth it to run the generator right here and get you all the way back up to the top, because maybe the next day is going to be a sunny day and you could have just waited it out and recovered the battery without running your generator. So is it worth running the generator, or is it worth buying more battery capacity? And so when we're designing an off-grid house, that's kind of where I hone in on battery bank right sizing, is saying, okay, we don't want to run the generator more than a few times a year. And so I'd say, okay, maybe the nickel iron battery vendor is telling me you could do a smaller battery because you can do a 80% deep cycle with nickel iron, whereas flood acid, even the industrial stuff, is really best to keep the deep cycling below 65%. And so you want to compare two batteries based off of what? How deep your recommended cycling is, and then cost. The way to connect all that together in off-grid sizing, I think, is the generator. So it's how often, if you downsize to a smaller battery that has a deeper cycle rating, you're still buying less capacity total. So how much more often are you going to have to run that generator or rely on the generator for electricity? So I've had customers who say, I don't want to rely on a generator at all. I just want the generator there for extreme weather events, and that's it. At which point we would increase the battery bank size to the point where we wouldn't have to crank the generator on these times. And so that's actually one way to determine what the battery capacity of your off-grid battery bank should be, is you can look at your solar production minus your monthly consumption. And again, because PV watts is actually simulating cloudy weather and sunny days, you can find how many days in a row you go without clouds, and then find what your maximum power draw or your consumption is over that time frame, and set that to be your 80% depth of discharge capacity, and that would give you the size of the battery bank you could buy to avoid running a generator altogether. And I think that that's a good inflection point to set, even when you have a generator, because keep in mind that the PV watts weather is simulating typical weather. And so they're, an atypical winter or an atypical summer, an atypical winter, you just might have a lot more clouds than you're used to. An atypical summer, it might be like there's a hurricane that's come in and put a 2-week-long cloud system on top of your solar array. And so I think, even if you're designing the system to not need a backup power system, it's still a good idea to have one there. Okay, so we're an hour and a half into our program. No, we're just a half an hour in the program. Yes. Lucky you. Okay, so now we can make a little bit more rhyme and reason out of battery spec sheets. Here's a battery spec sheet for lead acid, and what I think was kind of interesting about this battery line is here's a lead acid battery that's 6 volts, and we got these discharge rates: 5 hours, 10 hours, 20 hours, 100 hours. We got let's just go with the 20-hour discharge rate is 370 amp hours. And then there's a 2-volt battery line. Here we got down to 2 volts, and the amp hour capacity is 1,000 amp hours. these two batteries are the same size. And so for one, they've, for the same size, the same volume, they've really kicked down the voltage. And what that's done is upped the amperage. So they've assembled their battery chemistry together to keep the voltage low and keep adding amperage. We're going to get back to that point in a minute regarding the upper limit of how much you can store on a given circuit, because once you start pulling, substantial amp hours, 1,000 amps, your electric service panel is 200 amps. So if you're drawing 1,000 amps out of a battery, you're drawing, 5 times as much power out of your battery bank that, your electric service panel is rated for. And while that's all right, I mean, you're on the battery side, you're not on the service panel side. Your cabling is going to become utility scale sized cabling when you get down to amperages that high. So here we have two product lines. We got a premium lead acid and then an industrial lead acid. And if we go and look at their 2-volt industrial lead acid versus the premium line, the industrial lead acid is rated for a lot more amperage out of a 2-volt configuration than their premium line is. And so the reason why I mention that is, there's a quality difference between what a solar vendor might be marketing as a renewable or premium battery. And they say, yes, this is the battery that is made for solar. There's a whole nother step up in lead acid quality that is, I feel like the uptick is cost effective. Again, you would normally go for a premium line rather than an industrial line if you wanted the battery to not last as long and you were fine with the battery replacement and you just didn't want something with so much upfront expense. You would end up paying more per kilowatt hour over the life of that battery. But hey, some people, that's a valid strategy. 5 years on lead acid, see where lithium ion is down the road. So here's some dimensions of flooded lead acid, which is less dense than lithium ion. So lithium ion will take up more space, but it'll be, just as heavy. Now, what I'm trying to say is it's not like lead acid is heavy and lithium ion is lightweight. If you're doing a battery-based, a battery system for a building, it's going to weigh a lot. So here's we've used this battery before. It's rated for it's a 12-volt battery at 1270 amp hours. And so, a volt times an amp is a watt, 12 volts. And these are just nominal volts. These are just nickname voltages. We're going to talk about that a little bit later. The battery voltage jumps around a lot. So this is like about a 15 kilowatt hour battery if it's being discharged over a 20-hour period. It'd be less than that if it's discharged faster. And so this 15 kilowatt hour battery weighs almost 1,000 pounds. Now this actually started complicating our project logistics. When we ordered these batteries, we ordered 8 of them, and they came 4 to a pallet. And so each pallet weighed over 3,000 pounds, and 3,000 pounds is all you can fit down a lift gate. That ended up not mattering for us. We had some heavy duty off-road lift equipment because, as part of a residential new construction project. But the one downside of using, say, industrial lead acid is, or I guess you could say the same thing about pre-assembled battery pack options, is that they just get too heavy to ship. In this case, our lead acid batteries were 39 inches by 10 inches by 2 feet tall. So a little over 3 feet long, a little less than a foot wide, a little more than 2 feet tall. So there's, in National Electric Code, we got requirements for working space. You have to have, and I always try and say, don't try and memorize code. Try and understand, like, the reasoning that the code is there, and then that lets you better understand why the modifications to the rules exist. National Electric Code says, look, if you have electrical equipment that needs to be serviced, you have to have working space in front of that equipment in order to service it. And so in generally speaking, that means you have to have 3.5 feet of clearance from the front of the object to be able to stand in front of and work on it. And this actually fluctuates. It can be, if there's nothing behind you, it's like if there's electrical work behind you, if there's a wall behind you, if there's electrical equipment behind you, then the space can get, you might need to have 4 feet if there's electrical equipment behind you. 3.5 feet, I think, is if there's a wall behind you. The width of the working space is the same thing. It's really the width needs to be so one person can stand in front of the equipment and comfortably work there. And so, a person, you think about, okay, 2.5 feet, it's about 30 inches. And it can start from either side of the equipment. You just have to have that 30-inch requirement. And then there's a height as well. Someone has to be able to stand in front of the equipment and work on it. And so that's something to consider when choosing between, say, a lead acid battery or a lithium ion battery. So here's something that was given with our storage room. These are sealed batteries. In this picture, what's nice about a sealed battery is you don't have to service them. Whereas the lead acid batteries we ended up going with, let's see if I got pictures. Here's some examples. This is actually the nickel iron battery, but this is an unsealed battery. So see, these trays are to kind of capture and vent some gas to the outside. I don't know if I have any good pictures. Well, anyway, without spending too much time on it, the traditional lead acid batteries have little caps in them. And these caps need watering and emit gas. They're unsealed. And that means you have to be able to service all of these little point locations in the battery. And the only way to do that is to be able to have your 3.5 feet of clearance around this battery so you can actually lean over it and service it without having to lean, 3 feet over it. And so the battery space requirements for lead acid are pretty massive, because not only are the batteries 3 feet long, but then you need to have 3 feet all around it, which means just for the dedicated space for a lead acid battery, you're talking about, just for the battery itself, at least a 10-foot by 10-foot amount of floor space. And then your equipment walls start to get pretty large too, because remember, we're not just doing, a 7 kilowatt inverter for a solar array. Your electric service panel, how many watts is a residential service? We always know it's 240 volts, right? And we know it's 200 amps, right? A volt times an amp is a watt. That's 48, almost 50 kilowatts of power that's possible going through a 200 amp electric service. I tried to do this yesterday. Let me see if it works this time. No, what's going on? Well, that let the wind out of my sails. All right. Well, I'll deal with this after the break. We monitor this home. It's a 5,000 square foot electric house, and sometimes the demand on this home can get up to if it were uncontrolled. This electric home, just by itself, loads as high as 25 kilowatts, and they're not done installing everything. They could have a hot tub, and then the hot tub running at the same time as the oven, and it's a large home, and then really it was on the fence about whether or not it needed a 400 amp service. You got to think about a lot of these same kind of at least residential clients who are buying lithium-ion batteries and solar arrays. They may have electric cars, may have a higher electric demand. And so if we're talking about just one solar inverter being 7 kilowatts, to get up to the power requirements of just a typical large home, you may need 4 inverters worth of product. And if each inverter is 3 feet wide, you're looking at the electrical equipment taking up maybe 10 feet of space, maybe even more. This is for a system that's half that size. So we got 8 feet on our wall just for our 2 inverters. Our combined AC and DC service panel. These are the charge controllers that go into the DC side of the service panel. These are the inverters that go onto the AC side of the panel. We got a generator coming into the panel as well, and then an output to the home, main service panel. So just for kind of a average sized house, where the client is willing to do some energy management, you're looking at, the electrical wall needing 8 feet of space. And so what was kind of astounding to me is that we go back and look at the original plan for our battery room and ignore what the architect put in. We were originally thinking, we could just put all the equipment on the side of this room, and this room was about 16 feet wide. And it would have been a very tight squeeze, to say the least. And in fact, we ended up kind of, basically, another thing to keep in mind is Originally we were like, okay, well, if we don't have enough space, we might be able to overlap some of the equipment and hang it a little bit further up the wall, and tuck the batteries underneath. But actually, this configuration didn't work for a few reasons. One, we needed that walkway space on the other side to get around the batteries. And so, our system didn't work because we couldn't butt the batteries up against the wall. We had to back it out from the wall so that we could walk around and service all sides of it. Oh man, Phil, I'm sorry you're having problems with your sound. Um, hmm. Well, we do put the recordings of this on YouTube, so you can always email me if you continue to have problems and you need the course credit. Just jump out and send me an email, and we'll get you recording access. Anyway, so we needed the clearance space around our batteries, and our inverters went on the other wall. But now you have further space between your batteries and your inverters, so your cabling costs are going to shoot way up. Now, this is kind of funny. This is from the manufacturer's website, and they didn't maintain the 3.5 foot space between or the 4 foot space between the inverter and the electrical equipment. Another issue is you're not allowed, like is in this picture, to tuck the battery up against the wall and then have electrical stuff hanging above it. There's a rule that says, no more than 6 inches, 6 inches of space between, of depth. And so if our batteries are 3 feet long, and our service panel is only 8 inches long, you have more than 6 inches of difference between the two. And I don't think I tucked it into this program, but I have done some more thinking on this issue. And essentially, you might have seen in the news about some Tesla employees wanting to get into service panel configurations because of how much space kind of wiring everything together can get up to. The smallest option would be actually to build a box for the batteries and have clearance around each side with the electronics kind of hugging the perimeter of the battery. If you put it in a battery box on the outside of the building, a battery box on the outside of the building is the most space compact configuration. And if you are doing things like air conditioning it or putting the heating element in it for temperature regulation, you have the least amount of space to manage. Inside a room, this is it with 2 batteries. I'm getting back into the presentation here, but the point of it is that inside a room, you might not really have the space to do a code compliant flooded lead acid install because of the service requirements of the batteries, needing to be able to walk around the batteries and water them and measure their electrolyte level. In our off-grid class, we talk about how these maintenance tasks are really not that big of a deal. I'm not a guy who changes the oil on my car. Watering batteries is super easy. I mean, if you hate mowing the lawn, you'll look at watering batteries and say, okay, well, that's a chore I can do because you're just, they have watering kits that make the job real easy. And so, when I say lead acid batteries, a lot of homeowners are scared about the maintenance involved, but the maintenance tasks for lead acid batteries are very easy. Um, I guess the takeaway that I'd say is lead acid, again, good option for residential off grid when you're storing multiple days of power. But it is heavy, it's hard to install, it's difficult to site, and so it's just a very limited application. By the time you get into the commercial setting, for performance reasons, for space requirements, there's just too many reasons not to buy lithium ion. Um, this is just kind of some side information. When I wrote this program, we were building an off-grid home, and so I wanted to kind of introduce some of the things that we kind of encountered in this project. The first is we use these kind of metal roofing clamps to clamp solar to the house, and this isn't a solar program. I don't want to spend too much time on it, but the one thing we learned on this project is that the manufacturer recommends attaching to every single seam as you go across the roof. Every seam that the module transverses. So that would be, as opposed to most solar installers are used to having a very long span between attachment points, and so they might be tempted to skip over some seams and use fewer attachments. And the reason behind needing to attach to each seam is because of how the metal panel itself is attached to the decking underneath it. So it's not like you're lag screwing into the rafter, you're just attaching to the top of that metal roofing panel. And so to better distribute the uplift force across these metal roofing panels, you need to use more attachments. I mentioned that just because it's a common oversight that I see in design. And for that matter, clamping them to the standing seam metal roof is not a bad way to attach it. There's issues with using rail that, like if you get a bunch of snow on top of your array and your array is on an interconnected rack, it can distribute the load all the way at the bottom support of the rack on a slanted roof. So there are some advantages for getting rid of the rail that come with more attachment points. So I'm not trying to say that the railless attaching to the seam is the bad way to do it. It's what you do for standing seam metal rooftops. On a metal roof, it can be a challenge to transition the conduit into the roof. I don't like unsightly metal conduit running across the rooftop. Most solar fires that I have read about have been caused by rooftop cable management issues, kind of split between the DC wiring, but also the conduit on a metal roof failing with time, and the rough edges of the metal conduit then biting into these cables. And I think it's just good to get into the rooftop and transition to more, I guess a more controlled, less harsh environment than what you get with the roof because of temperature and thermal expansion on these metal pieces. Of course, on a metal roof, where do you enter into it? I usually just drill through the roof and use a pipe boot and make sure it's flash and sealed. In the same way a plumbing vent would transition through a metal rooftop. Although on this project, we sized our conduit and our entry points to actually go in through the Z-purlin through the top of the roof and transition then under the roof cap. And that worked out pretty well. They do make, metal roofing hoods or vent covers for doing the transition. And so this is a off-grid budget that I put together for this house. We spent, what was interesting is now the total budget, and this he installed it him, with his electrician helper. This doesn't include the labor that he hired. So at the end of the day, he took his about 4,000 square foot home off grid for a little over $80,000. I'd say 85,000. So we out of this budget, the battery bank was the most expensive. We ended up going with the industrial flooded lead acid. We went with 122 kilowatt hours worth, so that on the worst case weather scenario day, he would still have 20% left in his tank. That was according to PV Watts. And then and that was basically because, well, maybe, there was a battery technology out there saying that spend a little bit more money and you'll get a lower energy cost out of it, but we didn't really see it in our analysis. Of course, that was a few years ago. The inverter system is much more expensive than the inverter system of a solar array. So a solar inverter is one way. It takes the solar power from the module, from the array, and it squirts it into your electric service panel. And so for if you went and bought, this is two 7 kilowatt inverters. If you went and bought a 14 kilowatt solar inverter, you might get the 13 kilowatt solar inverter for $3,000 or $4,000 compared to $13,000. So yeah, I think that is something that can catch people by surprise is how much more you have to spend on your system components. But keep in mind a battery inverter. If it's a grid tied battery inverter, it's not only going to charge from the grid, it's also going to discharge into the grid. So already it's a two-way inverter instead of a one-way inverter. Like the solar array is a one-way inverter. Most battery inverters are a two-way inverter. Some aren't. Those grid assist inverters we talked about aren't. And generally, to charge the batteries from the grid, when you don't have a two-way inverter, you need to have a separate AC charger. And so a two-way inverter is going to have more components inside of it that are going to be more expensive than a one-way inverter. Like we said earlier, now that you are buying multiple inverters or inverters and charge controllers, you got to wire them all up together. And so you're buying a DC distribution panel, and you can't go to Home Depot and find a DC distribution panel. It's a specialty part. And you're lucky if you have parts that are part of a kit that can all fit nicely together. But you have to pay for that too. And we talked about all those other features that you might need to purchase as well that kind of fall out when you're doing a big project. But if you're just doing one battery inverter, you still have to buy all those kind of mandatory accessories. And so those costs just begin to skyrocket. So the inverters themselves are about 50, a little under 50 cents per watt. Whereas your solar inverters today are around 20 cents per watt. So your battery inverters compared to your solar only inverters are 2 to 2.5 times more expensive just for the component itself, and then require a lot more additional balance of system material. And so what's kind of interesting about that, again, this is a brand new product, so I didn't put it into the presentation, but like Outback, I just want to show you an example of how pricing these systems can be a little bit tricky. You know, here is an example of an Outback inverter that costs $3,600, and I'd say that's right in line with what it usually is. And it's an 8 kilowatt inverter. And so we're going to pull up and we're going to do 8,000 kilowatts, 8,000 watts. Do it the other way around. There we go. I'm going to do $3,600 divided by divided by 8,000 watts, and that's about 45 cents per watt. So this 8 kilowatt battery inverter, that's two ways, is 45 cents a watt. That costs more than a standard solar inverter. So then we go to Outback's brand new product, the Skybox. There you go, this will be a good one. So this is a 5,000 watt inverter, and it costs $5,600. So 5,000. The last inverter from Outback that we saw was 45 cents a watt. This one, costs $5,600, and it's only 5,000 watts. So it costs $1.12 a watt. So this Outback 5 kilowatt inverter, it costs 2.5 times as much as the Outback Radian inverter. So what's the difference between the two? Well, without it being too much of a product promotion or whatnot, the Outback Radian inverter is the inverter plus the required distribution panel plus the charge controller, plus the partridge and the pear tree, which lo and behold, when you sum it all up and put it all together, this is using Schneider instead of Outback, but what we ended up getting was about 14 kilowatts worth of inverter product for $13,600. I mean, when you sum up the charge controller, the inverter, the electrical balance of system material for these battery systems, at the residential level, at least, you can get up to $1 a watt. And at the commercial level, I would be budgeting 50 to 70 cents per watt for the inverter components, which is substantially larger than what you get with a more simple solar project. And so, maybe in the solar industry, we've gotten a little lazy with cheap solar components because, the battery components are going to put more cost back into the system. That's why, and I really hate myself for doing this sometimes, but that's why I have experimented with, and, I would still do it for my own house, but I'd think twice about doing it again for someone else. We're doing some experiments with this one, but we went and used the cheapest listed battery inverter on the market that we could find, and I actually got this one for about $3,000 because I'm the distributor. That's about 25 cents a watt. And so we see the range is you can get like a grid assist inverter that is not rated for grid tie. That is one way only. That is not interconnected to the grid. A lot less features, although Ames does a good job at building them in. At the end of the day, it's a cheaper inverter, and it's not really intended to run your entire house. Just smaller loads is 25 cents a watt. Then you get into the grid tie inverters like what we've been talking about, like Outback or Schneider or SMA, that get into 40 to 45 cents a watt. And then you get the balance of system material that comes on top of that. Let's see. Often these things will ship out freight. The only reason why this residential client was willing to spend so much money on his system was that he was facing $18,000 of grid interconnection fees, which very much sweetened the deal. It's going to be really hard to, and it may not be a good idea for customers to go off grid when they have the convenience of grid connection already there. That's going to that's going to be an individual's choice, and it's going to depend on where rate structures go in the future. If power companies start charging more fixed fees and don't give you, if more of your bill is a flat rate, less of it is a metered rate. They give you less of a metered rate down in the future, then you might, go off grid because of that. That we're not at that anywhere near that point yet, where optionally going off grid is more cost effective than remaining grid tied. Let's see. So this was just a smaller configuration, and that's kind of another interesting thing about what I've learned with battery systems is on the residential end, you really don't want to err in going too small. I mean, there's a lot of enthusiasts out there who are living on a 6 kilowatt or even a 3 kilowatt generator and telling you how great it is. But most homes today are going. I'd say 14 kilowatts is the minimum, and you really need to start considering larger systems from that point up. Unless you have a client that's really willing to embrace energy efficiency and energy management and live in a smaller house than what they can afford, I would say 14 kilowatts is the minimum starting size, and if and you need to implement a lot of load control for that too. Okay, so some shut off and shut down considerations is it can be really tempting to just wire the batteries straight up to the inverter. They have often these inverters have a big terminal lug that you go land your cable on, big terminal lug and go land your battery on. In the solar industry, we have disconnect requirements that have only become more strict with time. So, the disconnect on the outside of the building that the fire department can use to shut down, your energy services on site. Little boxes that go up, either right next to the solar array or underneath the solar array that, when the grid goes down, those boxes de-energize the solar array for fireman safety. The house is on fire, and you're fooling yourself to think that the likelihood of your house being on fire is less if you have a solar array and a battery. It's more. And so, these fire safety considerations are important, even if as installers we don't like them. So, you're buying, disconnect switches to go between each component so that you can service the component, so that you can, disconnect the generator and then service this line. Then you can disconnect the battery and service the battery. In the solar industry, it used to be that we had a 10-foot parameter around the solar array. And when a magic button was pressed, everything outside the 10-foot parameter was de-energized. Now that parameter has shrunk to be a 1-foot barrier with additional debate over what happens inside that barrier with additional shutdown requirements as well. And so when I look at battery disconnect requirements in code, I think that they're probably going to increase. The takeaway is right now you need at least one disconnect if the battery, and I guess the battery should have been pictured in this, but if the battery is within 5 feet of the inverter, you only need one disconnect, which is often going to be on the inverter or sometimes on a service panel, and then you go to the inverter. If the battery is more than 5 feet away from that disconnect, then it needs a disconnect on both sides of the strip. I think the knife switch requirements, I think they're actually adding them back into NEC 2020. Yeah, that's been a very common local jurisdiction requirement. And then installers were saying, now wait a minute, why do we need to have a knife switch on the side of the house? Can't we just have a regular disconnect switch? So I guess what this was saying is pay attention to some of this balance of system material, because a solar array already requires a knife, or in most cases already requires a knife switch. What we have now on this home is it's instead of doing a knife switch disconnect, we did a manual 3-way transfer switch. And so we have the grid coming in to one side of the switch, and then we have our solar off-grid on the other side of the switch. And so for a few $100s more, instead of just having 2 knife switches right next to each other, we were able to combine it together. I don't know. That's more of a solar topic of discussion. I think what I'm trying to say is for the battery disconnect switches, we don't have requirements to, like, within 1 foot of the battery bank have a disconnect switch where the fire department can come in and press a button and open up that kind of switch system. But I expect that it'll come into National Electric Code over the years to come. DC wiring when inside a building needs to be in metal conduit. A lot of battery banks are inside the building. If they're outside, in a non-habitable battery box, they can be in plastic. If it's inside the building, it needs to be in metal. And so, DC wiring is common in EMT conduit. You can get it in a flexible metal conduit. Battery rooms that have sealed batteries are subject to corrosion. The gas that comes out of a sealed battery can corrode the metal. And so, what I like doing in lead acid battery rooms is get my flexible metal conduit with a plastic coating on it, liquid tight flexible metal conduit, or liquid tight conduit. But sometimes the liquid tight conduit doesn't have the metal inside of it. So the inspector on these indoor battery banks is going to see the cabling in metal conduit. It's really more for physical protection of the cable than anything else. Yeah. All right, so let's take a look at some of the greater look at some of the battery balance of system material. Um, these are expansion boxes that you get with stackable inverters. So if I have one battery inverter that's 7 kilowatts and I want to get a second battery inverter that's 7 kilowatts, it's very common for the manufacturer to supply a wiring kit for connecting one to the other. It's important to note the breaker sizes and breaker types. Sometimes with the battery system, you get into these high amperage DC breakers that can be kind of hard to find. So generally, you're buying breakers from the inverter manufacturer or the inverter supplier. Let's see. Now down here it says 1 pair of 4-aught battery cables. Here's our charge controller. This does the DC from the solar to the battery bank. Although you could also use a charge controller, I guess, from the AC from an inverter output. It's the inverter, the AC to DC inverter is still doing some voltage regulation. Anyway, here's a spec sheet for our 600 volt charge controller. It's shown that it'll work from an array operating voltage of 200 volts to 550. That the nominal battery voltage, the default is 48 volts. So here's another thing: is a lot of these DC components might be listed for multiple voltages, like 24 volts or 48 volts. If you see that it's listed at 48 volts and it's a 80 amp 600 volt unit, often when you put it into the 24 volt setting, it's not like the amperage is going to magically double and be rated for 160 amps instead of 80 amps. And so what that means is if you operate it in its 24 volt setting instead of its 48 volt, if it's cross-listed, that usually will mean that you'll only get half of its rated capacity out of it. Battery voltage operating range 16 to 67 volts DC. That's kind of interesting. Remember we talked about yesterday how unsealed flooded lead acid voltage can get up to higher voltages than sealed lead acid. When you buy a charge controller or a battery inverter, it'll come with different programmable settings. One for lead acid, one for lithium ion. And essentially what we see is the lithium ion charger settings are less aggressive than the unsealed flooded lead acid. And so a lithium ion charger may cut out at 58 volts. Whereas when you do use the same charge controller for a lead acid battery, you will program it, often be charging at a higher voltage than that, especially during battery maintenance. During battery maintenance, which is when you're applying the highest voltage to the battery to kind of clean it, you're generally doing that around 63 volts on a 48 volt nominal for unsealed only. Let's see, we got maximum charge rates, maximum and minimum wire sizing. I usually will just look at that and kind of use the thickest cable gauges anyway. And then support for different kinds of battery technologies. And generally what that support means is it is for sealed lead acid, and there's a couple of different kinds of sealed lead acid. Also for sealed lithium ion, it'll just run it at a less aggressive charge than with unsealed batteries. Another thing that was interesting to me about battery components compared to solar components is the warranties are much shorter. Solar, we've gotten spoiled by 25-year module warranties, and inverter manufacturers who are striving to reach the same number for their component warranties. In our solar class, we talk about how a 25-year solar warranty is not always a 25-year warranty. Sometimes the build quality is only warranted for 10 years instead of 25, and it generates this kind of illusion of a 25-year warranty. Well, battery warranty, component warranties are often 5 years. Sometimes they're 1 year if you're going real low end. So that was kind of a shocking difference. All right, so monitoring is interesting. In a battery system, you want to monitor not just the output from the solar array, but also the load. And so you're going to need more than just your inverter monitoring system. We're going to take a break in a few minutes, and I'll bring up what we're doing for our monitoring after the break, so you can kind of see what we do for off-grid homes is build our own monitoring system. Commercial inverters. Essentially, all you're doing is installing a monitoring system, not just for the battery and the inverter, but also for the building itself. There's a few different ways to do that. And so we've talked about these little monitoring units. There's this one is a voltage sensor on the battery that will track the battery voltage to a high degree of sensitivity to better gauge battery life. This battery accessory was a programmable control unit, which I thought was kind of a weird thing not to include. But if you didn't buy it, then you couldn't program the inverter. So, at the same time, you don't necessarily want your client to be able to just reprogram their system willy-nilly and mess it up. But anyway, it's one of those mandatory accessories. All right, so when you're building, say, an off-grid house, you actually don't have to give them standard electric service, although to stay on home base, doing a 120, 240 volt electric service is typical in the US. But if it's a smaller house, then maybe you could get away with 120 volt circuits only. If it's a larger house, you're not absolutely crazy thinking that it might be better to go with a 3-phase battery inverter, as they'll do in other countries. One thing you need to look out for is sometimes the battery components are not geared with your particular electric service in mind. I think a good example is SMA, where their battery system, the standard unit, is a 120 volt inverter rather than a 120 240 split phase. You actually have to buy 2 of their units or use a transformer to get up to 120 240. Likewise, a lot of the 3-phase, especially for small commercial 3-phase inverters, will basically be the single-phase inverter, but you buy them in groups of 3. this is kind of a smart home thing that I've installed on the house where I'm currently giving the webinar. And what this allows us to do is look at the load profile of the house. We actually have two graphs here because we have two different floors of the house, two different service panels, and ultimately right now we're running them off two separate inverters and keeping the panels separately derived. That was mainly a cost-driven decision because if we went with an off-grid grid assist inverter, we could get the price point down so that our what it was is about a 12 kilowatt inverter for $3,000, whereas anything that was a grid tied or grid connected inverter would have cost, as we saw earlier, anywhere from two to just the inverter itself costs twice as much. But the problem is, now we have some loads that are exceeding the inverter capacity. And inverters do have, battery inverters have a burst mode. So that for a few seconds, up to about 30 seconds, they can burst to 2 or 3 times their rated capacity, assuming it's going to drop down again. But once that burst mode continues for about more than a minute or so, it drops off. And so if the load is, say, a 15-minute load, and then it drops down again, and it's above what the inverter can handle, that's going to just disconnect. The inverter is going to shut off, disconnect. And so what we're looking at today, when we're not in class, is that the electric heat pumps have electric heat strips inside of them. And so what we've done is we can see like the heat pump turn on, and then the heating strips turn on and skyrocket the load. So we're trying to, in our case, we're looking at our system, and we have two 12 kilowatt inverters feeding each floor. And for the next phase in our construction, we're saying, okay, do we have X amount of dollars to spend? Do we spend that on buying, more inverter capacity and maybe just a small battery to serve these peak loads? Or can we use the same amount of money and just take our lead acid battery and only use it to power, the basement, and then put the upper floor, which is a much more volatile floor. It's funny. We have all of our computer equipment in the basement. So our base load in the basement is actually higher than what it is on the main floor. But because the main floor is used more often, and because the air conditioning system is spread, and that's the main floor is on the main floor service panel, we can see that the main floor is much more erratic. And so battery inverters can see the same data to do load leveling. And what's kind of interesting about the not the bargain bin battery inverters, but the ones that most solar installers are using, quality battery manufacturers like Outback or Schneider or SMA or Magnum, and Tesla for that matter, and there's more to come. Most of these are multifunctional. Like a grid-tied battery inverter is often multifunctional. And so you don't have to have it be powering your house in an off-grid mode. You could have it be powering your house just for peak loads. And so, when it sees this kind of data, the inverter, you can have a standalone battery inverter that comes and says, okay, we're going to turn on only during this time and serve that peak load. And that would actually make it a lot easier on our flooded lead acid battery. Because again, it's not, it's not that this load itself would, if it were on for 6 hours, it would fully discharge our battery. But we know it's not going to be on for 6 hours. And so, it's not going to fully discharge our battery, except during that time when it is on, it's going to be really hard on the battery. That load might be pulling twice as much energy from the battery than if it were the same amount of energy being pulled over a longer period of time, because lead acid is not good for high discharge rates. And so you can take, pretty much any battery inverter that can synchronize to the grid can connect to, your power signal and turn on and load level. Our problem is, on our site, is we went with the cheapest inverters we can use, which per the inverter manufacturer instruction are non-stackable. What that means is, they're the battery inverter that puts out its own signal. A synchronous battery inverter can synchronize to that signal. But if you put an asynchronous inverter on an asynchronous inverter, then you're gonna have, you'll know your electricity will no longer work. It'll be out of phase. And so it's a danger for us. What we want to do is figure out how to do some load leveling without buying that additional inverter, because our manufacturer is specifically telling us that they will not support their product if we add another battery inverter to it. So I think I just muddied the waters a little bit on a quiz question for today, which is, can you connect any battery inverter to any other battery inverter? The answer is no. You have to be very careful if you do, and at the very least, the battery inverter manufacturers may take that as an excuse to void the warranty. But it's not that it's impossible to do. It's just, when I say the answer is no, what I mean is right off the bat, the answer is no, unless you can prove otherwise. And what it is some battery manufacturers will sell synchronous inverters, but they only want you to stay within their ecosystem. So they don't like it when you use another manufacturer's product on your own, even if you're physically capable of doing it. At the same time, if you just take two battery inverters and they're both in their master mode, they're not in the synchronous mode, they're in the master mode, they'll fight with each other, and one of them will burn up, and they might burn up your other electrical components too. So while I say, our solution is just to, add more inverter capacity, we have to proceed with caution, because we have to make sure that our battery inverter is synchronous to the generator, to our baseload generator. When you get into more advanced and more expensive inverters, they can actually, the upgraded electronics helps. What's missing in this graph is solar production. I guess that's kind of a bad. What this is 9 a.m. The sun starts coming up and peaks around noon and starts to tail from there. Anyway, we're going to come back to this when we talk about load control. But the takeaway is it's just not so easy as to just stack one inverter from another inverter. What some battery inverters will do is they will fake just for a split second, not enough to blip your electricity, but enough to trigger the alarm protocols for a grid shutdown and your other grid tied components. So that if a solar array was producing too much power and the batteries were already fully charged, and the battery inverter was concerned about being backfed and not being able to produce its signal and the grid part collapsing, it could briefly shift the frequency of its output and juke the solar inverter into turning off. But like my off-grid inverter doesn't have that capability. And so there are higher quality battery inverters that can play nice with anybody's solar array. But battery inverters will often not play nice with another manufacturer's battery inverter. And it's not that you can't program them to actually do so. It's that if you do that, neither manufacturer will support their warranty. This was the Tesla Powerwall 1. It was a 6.5 kilowatt hour battery. The Tesla Powerwall 2 is really just two Tesla Powerwall 1s. But this is what we're looking at. So its specs is 3.3 kilowatts and 6.4 kilowatt hours. And so when we think about lithium ion not really performing better than at a 2-hour discharge rate, anything less than that starts degrading its performance. What we see is Tesla, by providing the inverter and the battery, has kind of made it, idiot proof to say that they're not going to allow you to discharge the battery any faster than its C2 discharge rate, by limiting the hardware. Okay. What that means is to power an entire house, if your house needed, conservatively 20 kilowatts of power, you're looking at needing to buy 6 or 7 of these Tesla Powerwalls. And then the storage capacity, maybe in line with a day's worth of storage or so. The problem with that is it just gets pricey. Okay, so what's kind of interesting is Tesla is advertising their battery at 100% depth of discharge. That isn't completely true. They hide a little bit of reserve capacity that you don't get access to. If you completely discharge a lithium-ion battery, it actually won't charge back up again. That's compared to lead acid, that if you completely discharge it unsealed, you may be able to overcharge it and condition it back to life. And so Tesla is taking almost like the Apple approach, where they're designing their product to not do everything that Droid can do, but maybe deliver a better overall user experience. Another thing to keep in mind is, even though Tesla is saying you get 100% depth of discharge, you may want to check up on the warranty terms and conditions, where you might get other guidance as to usage parameters, as we've seen with their rival Simply Phi, that gives you, a different cycle rating for, 80% depth of discharge versus 90 or 100%. A 10-year warranty. We saw how it's either a 10-year warranty or a certain amount of kilowatt-hours output, whichever gets you there first. And so what they're saying is, we're going to give you a 10-year warranty on the battery, but if you fully cycle it every single day and you only get 3,500 cycles out of it, it might actually turn out to be an 8-year warranty or 9-year warranty. But if you don't use it heavily, then it'll be a maximum of a 10-year warranty on our end. But that is to say, if you take a lithium-ion battery and it's rated for 3,500 cycles at 80%, and you only deep cycle it to 40% instead of 80%, you can reasonably expect the battery to last twice as long. With lead acid, it gets even more, not just twice as long, maybe 3 or 4 times as long. We see that the Tesla battery is operating at high voltages. Now, if you open up the battery, it would be contained of individual cells at lower voltages. So theoretically, you could take apart a Tesla Powerwall and make a couple of smaller batteries out of it. The output current is 10 amps. A 200 amp service panel, to become equivalent to the full amperage of what the grid could provide, you would need 20 Tesla Powerwalls. And so to avoid, the only way you can legally design a system that is going to be the main power supply for a house is to supply the full load. You're putting a 200 amp service panel in there with a 200 amp breaker. The question becomes, do you need to put in 20 Tesla Powerwalls to supply the full amount of amperage? The answer is no, you don't. But if you don't, you have to have load control. So we can have temporary backup power, not feeding our home with the full amount of amperage, and you won't be able to use every appliance in your house. But the homeowner should reasonably expect his appliances to work when he moves into the home. So you have to supply him with a certain amount of power. And every home is different. An all-electric home is different than a home that's not all-electric. So here we're seeing, this maximum load being about 20 kilowatts, and that could easily occur without load management at the same time as the other heat pump coming on, and that would be, a combined temporary load of about, 30 kW. Or you implement a different heating strategy. I mean, the problem with these heaters are that the electric heat is kicking on before the heat pump does, in order to kind of like supercharge the heating in the morning. But now we need to figure out how to reprogram it to kind of disable that electric heat strips. Let's see. So they're saying they got a single phase and 3-phase compatibility, rated for indoor or outdoor installations. Some dimensions of it. What's kind of nice about the Tesla one is they've designed it to be only 8 inches deep. And so you can kind of hang it on the wall. I've seen a lot of garage walls become Tesla Powerwalls. You can't do that with lead acid. This is just a different battery inverter. This is the Schneider battery inverter. It's 6,800 watts. And we can see that for 30 minutes, it can actually output 8,500 watts. And then for 60 seconds, it can output 1,200 watts. So it's quote unquote burst capacity is, about almost a little under double for 60 seconds what it can do continuously. And so, we do get a little bit more capability out of the inverter for short term, but not for long term. If you're monitoring, loads that are lasting, this is actually after we adjusted the thermostats to stagger. It was earlier. It was just a big 30-minute load that was that long. The inverter couldn't take it. But if the load gets down to about, if we're looking at a 12 kilowatt inverter and we're asking its burst capacity of about 20% or so, we can do that for a few minutes. The Schneider inverter is giving you a burst capacity of 30% or so for 30 minutes. Now, my cheaper inverters, you get over that load for more than a minute and it cuts off, which is you get what you pay for. Let's see, total harmonic distortion at rated power is less than 5%. I have noticed the power quality of battery inverters to not be as good as most electric grids. Again, this is an element of getting what you pay for. If you use a flooded lead acid battery and the cheapest battery inverter, you're going to get more harmonic distortion than a lithium-ion battery with a top-shelf inverter. So, particularly for the off-grid cleaners, where this comes up as an issue is LED lighting circuits. So you really want to make sure you're using high-quality LEDs. I would say, if you're going to have any kind of active battery energy system on your facility, if you're going to have a battery that's going to be dumping energy into the grid during peak times, or if you're going to be doing residential off-grid, residential, the volatility can get even worse because you're going to have some electrical appliances, and the heavy duty ones, when they click on, there's only so much load leveling you can do with an electric oven. It's either on or it's off. I mean, you could run it on low for longer and high for less time. That doesn't really work when you're just trying to have Thanksgiving. And for example, my tank water tanks. It's like, well, I thought, if I have a tank water tank, that it would use a little bit of heat over a long period of time, as opposed to a tankless heater that uses a lot of heat over a short period of time. Well, starting to look at it, the electric water tank uses, not as much as the tankless, but still a lot of energy over a short period of time. Like that might be the water tank right there. So I guess, I don't know, if you have power quality issues, that's been our biggest issue so far, is just LED flicker. Not in every circuit, but it kind of seems like when the charge controllers are kicking in or the power is surging, and it causes a slight voltage ripple in the battery bank. So we have input DC voltage range, 42 to 60 volts for the battery bank. Capable of charging up to 64 volts. You really won't charge if you're doing a 48 volt lithium ion bank, you won't charge that more than 60. It's the lead acid that needs that slightly taller range. Battery temperature sensors. The charge rate of the battery does vary with its internal temperature. And so, it's just simple. It plugs in almost like with a telephone jack. It just plugs into the inverter and you stick it on your battery so that it, basically will tell it if it's a cold battery or a warm battery or a hot battery, so that it doesn't overcharge it. On a cold day, the battery and the voltage rises in the battery. And so you would have to be careful not to overcharge your battery on a cold day a little bit more than on a warm day. Power factor corrected charging, it's not a unity. Then we get to our battery bank range and size. There is a minimum amount of batteries that they want you to put on the battery inverter. So if we look at this Schneider one, for example, it's a minimum battery of 440 amp hours, and nominally it's a 48 volt battery bank. And so what they're saying is, hey, the smallest battery we want you to put on our 6,800 watt inverter is 21 kilowatts. You say, well, is that really true or not? And they're going to say, it's our recommendation. What we know is that for a lithium ion battery bank, 6.8 times 2, we might be able to get away with, a 14 or 15 kilowatt hour battery bank. On a lead acid, if this were lead acid, a 6.8 kilowatt load, we'd want at least 6 hours of capacity on that. That would be, Schneider's saying is, you could put a 21 kilowatt battery on it and it'll work, but that doesn't mean you can't, blow it out if you're running that 6 kilowatt load consistently throughout for, a solid period of time. And so I think as you're designing the battery, the more data you can have on your customer's load, the better, because when you're modeling it, if you can start fitting your energy usage to a narrative that helps you diagnose, that'll help you with your model. Let's see, this inverter has different inputs for a grid input versus a generator input, so it can switch between two sources. Adjustable frequencies. So these are often international products, and so you might have a dip switch or a programmable item on what frequency it's on. Always useful to check before you commission. Okay, so here we're getting into some more advanced battery inverter configuration options, like the grid cell range, or the grid cell voltage range, or the grid cell frequency range. So these are different ways you could use the battery inverter. The frequency range, that's something that only like power engineers will really understand. You might be able to program the inverter to stabilize the frequency by discharging the battery when the grid frequency starts to jump. I can help you with power quality issues. Current or voltage would the difference would be, it says, okay, we'll sell when the battery is reaching a certain state of charge, or sell when the facility is pulling in X amount of current. And so those might be different considerations for, okay, let's say you're a solar owner and you want to sell back surplus production to the grid, but you also want to make sure that you're keeping enough reserve capacity in your battery so that you don't sell too much back. You want to be there, have a little bit for a power outage. Or you're a building and you want to do demand management, you would be looking for current limitations, so that if I'm pulling in 200 amps of current from the facility, I know I'm pulling 50 kilowatts. If I have programmed the inverter to not do more than 50 kilowatts, it would be saying, okay, whenever our facility current is more than 200 amps, that's when you discharge the battery, and only at that time. So when you get out of the bargain bin, you get into products that are kind of designed both for the residential market and for small commercial. And furthermore, there's a different product class for large commercial where, like, even Tesla, instead of selling you power walls, they'll sell you power packs, which are just larger, more dense, heavier power walls that are better scaled for commercial installations. Let's see, environmental ratings, that's something to be careful on. A lot of battery inverters are not, they are assuming that you're not dumping your expensive battery stuff outside in direct exposure to the sun and wind and rain. Solar guys, we're kind of used to doing exactly that. We're working on top of the roof. Um, and we're used to getting nice outdoor rated stuff that we can just bolt on the outside of the building and be done with it. It's best for your battery stuff to be weather protected and environmental controlled. And in fact, some battery inverter manufacturers are assuming that that's what you're going to do, and so the environmental ratings of these inverters are not always the like what you would expect in the rest of the solar industry. So here we have different modes, operating modes. Um, Grid sellback, peak load shaving, generator support. That's kind of an interesting one where, let's say, getting back to our home, if this was a truly off-grid situation, we're actually doing grid assist, and so when the loads kick in and the batteries are depleted, the grid can bypass the system and supply the loads. But if this were an off-grid situation, we, instead of having the grid, we would have a generator. And so what this particular inverter says, it says, look, we have a grid assist mode so that when the load ramps up to a certain level and that would exceed the discharge rate limits of your battery, we'll turn the generator on and have the generator assist those loads as well. Prioritized consumption, we use that in grid assist, but it's not just a grid assist feature. That would be where your goal is to not export energy onto the grid, to prioritize using the battery to the fullest extent before selling anything back. That would be as opposed to a zero export mode where under no circumstances can you outflow onto the grid, which is something they do in Hawaii, because all the homes in Hawaii already have solar, so they're already experiencing issues related to solar outflow. Not a problem we have in Mississippi, where we don't have much solar, but it's a problem in other areas where they do. And so we also saw that this has an interesting one for frequency control. And so here's just some pictures of stacked up residential inverters that can scale up, all the way up into small commercial sizes. And so, like, here's Outback, and Outback now has two other product iterations, but this is kind of their standard one. And what they have is a AC panel, and then a little AC expansion bus bar, and then a DC panel and a DC expansion bus bar. And so we're coming out the DC side with our charge controllers. All these charge controllers are landing on their individual breakers and then being bussed together. And all the DC side of the inverters are being bussed together. And then kind of the same thing on the AC side. The AC outputs are being paralleled together with overcurrent protection in these breakers before being outputted at one point to the load. So very scalable, very stackable. This is SMA system where they do the same thing. You Magna's system where they do the same thing. Well, let's look over some wiring diagrams so we can kind of understand what's going on here. Here we have two battery inverters that are coming off a single battery bank, and then we have the AC side coming in, a load panel here, and this would be a backed up critical load panel. So let's say you had this is a grid tied system. You might have your main 200 amp load panel here, and then this could be 100 amp load. We're assuming this is a 7 kilowatt generator and a 7 kilowatt inverter. So if you're really thinking about like home design, I kind of think it's interesting that maybe the best solution is to have all these residential inverters and small lithium-ion battery banks are really better geared towards protecting critical loads, and it's pretty hard to pull off. Like you can't pull a 200 amp service panel off of a 200 amp service panel. So, it's a lot easier to back up a 100 amp critical load panel than it is a load panel for your entire house. And so maybe, an optimal configuration is to have, the home's service panels, which are traditionally just distributed on one 200 amp panel, to be instead distributed across 2 or 3 100 amp panels, each with their own battery backup and each of their own inverter. Let's move on. We got some more detailed wiring diagrams coming up. Let's see. So here's the underside, some knockouts. One thing that's kind of interesting to know about these knockouts is you really want to use the outer ring if you have a choice between the two. Not only does that allow you to use your EMT bushing and ground nut as a ground path without a grounding bushing. If you use the inner ring, it's this metal to surface connection is considered weaker, so it doesn't serve as a ground path. It's also easy to knock the inner ring out by accident. So, when you're choosing your conduit and looking at it, I like choosing my conduit sizes based off what this outer ring size is, regardless of if I could have gotten away with a smaller one. Here's the battery terminals, communication ports, and auxiliary sensors that might be used to send a relay to start a generator. Now this is kind of what it looks like inside the switch gear. So here we have batteries where usually you're crimping these ring terminals that are very thick. I'm using a crimp tool and a sledgehammer. There's industrial crimping tools for battery cable that's this thick. We're talking about, we saw how, the manufacturers are just shipping it with 4/0 cable. This is cable that is a few bucks a foot. And so here we have our circuitry, our positive and our negative. This is our negative here, and we see our positive on a positive breaker landing on the positive bus bar, still in its own ring terminal, on a ring terminal in the inverter. So, so often you'll be making these wires on your own, but some manufacturers will sell these as kits and assume, a 10-foot length, since there shouldn't be more than 5 feet between your battery bank and your inverter. Without this disconnect switch. If there were, then you'd have to land on, another box with a disconnect switch before landing on your battery. So this is just in case there's people wondering. This is a bus bar. A bus bar is a piece of metal that you can lug onto, and there's only certain circumstances then you're allowed to do that. For instance, if you're using multiple circuits, then you need to have some overcurrent protection in case one of the circuits tries to overpower the others. Let's see. So now we're getting a little more complicated. This is the same system as before, except instead of having just one inverter, we have two. And so, when you're double stacking inverters or wiring up charge controllers to the same bus bar, or if you wanted to add a super capacitor, or another string of batteries, every time along this bus bar, you're going to need, places to land these circuits. Again, that starts getting you into, needing boxed into buying these specialty balance of system materials. It's hard to find bus bar bits and pieces. And so here we have the two inverters being wired in parallel to each other, sharing the same ground, wired together on the bus bar so that you still just have one circuit being pulled off to the batteries. So the batteries are wired to the bus bar, the inverters are wired to the bus bar, the inverters are wired to the bus bar. So now this is a little more complicated. We still have two inverters, and they've kind of grayed out the whole bus bar wiring to the battery area. What we're looking at here is the inverters being wired, and there's a grid connected load panel. And these are bidirectional inverters, so they are rated to backfeed the grid and feed the load panel and then feed the grid. So, even though I say this is a grid connected panel, what happens during a power outage is the grid tied panel turns off, and then a transfer switch that's in the inverter will power the critical load panel. And so the thing about a critical load panel is it can only be rated for what the inverter can output. So like some like we saw the Tesla Powerwall only being able to output 10 amps. And so usually the Tesla Powerwall is just trying to output all of its power into whatever will take it, sell it back to the grid, put it into the load. If the grid sellback rate's not very good, it'll just slowly discharge that you'll still use the power. But something like the Tesla Powerwall, just one of them outputting 10 amps, that is not enough to power an entire house. And even a critical load panel is, let's just call it 100 amps. It's not your whole house. And let's not kid ourselves. Customers buying batteries and solar and spending lots of money, they really want their whole house to be powered. But it's just hard to do that because this stuff's expensive. I've been down the road to try and make instead of buying two stackable inverters, buying one cheaper combined all-in-one unit. And it's not something that I'm excited about doing again in the future, just because anything that goes wrong in off-grid, it's harder to, it's a more important problem than if you're grid connected. So using bargain bin stuff is not something you really want to do for, you might do for yourself, but I wouldn't recommend doing it for your clients. Anyway, let's use this to talk about kind of a problem I had on a battery system. We did a large enough system where we added another inverter here that we just got rid of any kind of grid tied panel and ran everything off our critical load panel. The whole house is off grid, critical load panel. And that's because this was a true off-grid house. We didn't have access to the grid. And it was a well-sized system with a well-sized battery banks. It's what we saw in the example between today and this morning. And so we put in a 122 kilowatt hour battery bank, and then we went and tied into the DC side with charge controllers, a large enough solar array to fill those batteries back up. And so the problem became the system worked so good that we didn't need to really use the generator. Well, then the homeowner, moved into the house full time, started using their electricity more, and started using the system effectively, and started to say, you know what, when we go a couple of days without sunlight, we want to use the generator. We want to turn the generator on and charge the batteries back up. Well, what was happening was we were turning the generator on, and it was going through this whole mess of switchgear and powering the load, but it wasn't charging through the inverters out the DC side. It wasn't charging the battery. And so just to kind of reiterate, the power was coming out of the generator and going into the top here. And the inverters would normally be powering and their AC side coming out the bottom, and they'd share this bus to come out in the middle, which would then go to the load panel. And then separately, we have some grid type connections that can go out and power the grid. And so what we had in our circumstance was the power was coming out of the generator, going through this switch gear and powering the service panel, but it wasn't charging the batteries. And so our question was, do we have a switch so that the grid or the generator is cutting out the batteries and just directly powering it? Or do we have, is it, how is this working? And the problem is these generators are multifaceted. You might have a grid assist system where, the grid and the solar array cannot be interconnected at the same time. And it might be perfectly appropriate to let the sun come back up and charge up the batteries and just run off grid power in the meantime, or generator power in the meantime. You're not really saving too much gas by using the generator to charge the batteries versus directly drive the home. There's nuances to that, but we're talking about minor efficiency gains, not major efficiency gains. And so we started to look at this and said, no, this is landing on a breaker, and that breaker's on, and the generator's on, and so we should be able to draw power from the generator back through the grid input or generator input of the inverter and send it back out the DC side to the DC bus bars and use that to charge the battery. And it turns out the problem was there's a setting inside the inverter, separate settings for the charge rate of the DC side charge controllers, and a separate charge rate setting for the AC side generator, which we hadn't enabled. And so, I guess what I'm trying to say is that the generator can charge the batteries, it can power the grid, it can be isolated from the system or connected to the system based on the needs of the project. So here is a system where we got two charge controllers that are taking the fluctuating voltage from the solar array. That can jump up and down to as much as 600 volts during the day or 0 volts at night. Cloud passes over the array, this voltage jumps around. The charge controller tries to take fluctuating voltage and send a steady voltage back to the batteries. One thing that was different about battery systems versus pure solar arrays is solar without batteries. It was all about just taking all that power and then dumping it all into the grid. Unless you're programming the inverter to take the power out of the battery and dump it into the grid, that battery will just stay there. So, they call it the difference between voltage sourcing and current sourcing. But the takeaway is, rather than dump all of the solar array's power, the charge controller is only going to output power to charge the battery, and that's it. So unless you're programming the inverter to sell, it's just it's either that or you're going to have wasted energy up on the solar array. So that was kind of interesting. I'm used to solar always being on, because it's either going into the load or being sold back to the grid. And I had to remind myself when I'm diagnosing, issues on my battery system parts, you could put your amp meter around your solar conductor coming from the charge controller to the battery in the middle of the day and not be getting any power. Like, well, why is that? It's like, oh, because the battery is so full and the home load is so low that the charge controller is saying, I'm not charging the battery until it needs it. Okay, so here was a project where the homeowner didn't want to do a battery just yet. They had enough money to do a nice solar ground mount, but we're looking at battery pricing and said, you know what? Battery pricing, it's supposed to drop. I'm going to wait for it to drop before adding batteries. So I've done this with a few customers, kind of expecting that there will be a phone call in the years to come when they say, okay, well, let's go ahead and add one. And so, this is SMA's system. And an SMA system, it's pretty straightforward. They just sell another battery inverter, and that would be wired, AC coupled. SolarEdge actually makes a battery enabled version of their existing inverter. So sometimes we would buy the battery inverter and not install the battery. So I guess what I'm trying to say in this slide is, what is the minimum amount of money you must spend on a battery system simply to say, I have it if I need it? And keep in mind that if you're not going for the whole house off grid, if you're just going for having it when you need it, you're still not talking about a whole house worth of power. You're talking about like what can I spend to at least somehow use some of my solar array during a blackout? What's the minimum amount of money I can spend to have some electricity during an emergency? But you're still going to be constrained by the output capacity of your system. So let's just take like a typical home that already has a solar array attached to it. Basically what you'd be looking at is, a DC side distribution panel, or if it's AC coupling, an AC distribution panel, if the battery is integrated into the inverter, such as the Tesla Powerwall. And so you're going to need a distribution panel. You may or may not need those monitoring accessories, or you will need those monitoring accessories. And then you'll either need to buy a charge controller or a battery inverter. So either you do a DC coupled system with a charge controller and wire it up to your I guess you're going to need a battery inverter and anyway, you'll either need to throw out your existing inverter and get a battery inverter, or you'll need, at the bare minimum, you need to get a charge controller and a battery inverter, or a battery inverter and a solar inverter. Or you could say, okay, well, what if I got just one that was completely integrated by itself, like the Skybox, and you're paying $1 a watt for that. And so what I would say is you're looking at in parts, compared to a residential solar array, to add battery capability to any residential solar array, you're looking at spending around over $5,000 just on upgrading the inverter and buying the appropriate balance of system material before you buy the battery itself. And so then you go and look at like the SMA's minimum battery inverter size or Schneider's minimum battery inverter size. We had previously talked about 440 amps at 48 volts. You could get away with keeping it at a 24 volt system and dropping that down to 10 kilowatt hours. So anyway, what we then selected was the cheapest brand new sealed battery, which is AGM, lead acid. So we're back on lead acid. Why are we talking about lead acid? This is actually a entry level lead acid. It's not a good battery. It costs over 20 cents a kilowatt hour to run. More than a grid price of electricity run. But remember, this is just a battery that you're actually never supposed to use. This is just something that's going to sit back and hang out and just be there during a power outage to turn on the array during the day and protect a critical load panel at night. So you're looking at, to take a solar quote from a batteryless solar quote to a battery solar quote, minimally adding $10,000 to the price of the system. So, batteries are not inexpensive. You look at the minimum amount of money you need to spend to add any sort of battery to a system. To a batteryless solar array being about $10,000. You say, okay, well, is it really affordable to go off grid? Even if you're mad at your utility for charging you $30 a month as a meter fee before you buy a dime of electricity from them, $9,000 for a small battery, that really won't even take you off grid. just saving that on that meter fee alone is not going to get you to the point where you're going to disconnect from the grid. And so maybe you don't need a large battery. Maybe you just need a small battery for power outages and a little bit of battery inverter capability and stay grid connected. And you're not really buying the battery for economic reasons. You're going to get a little bit of backup power for about $10,000. Okay, so yesterday, zoom in here a little bit. Yesterday, we were talking about kind of more exciting applications of batteries. Having the customer spend 10 grand to get a couple hours worth of home power during an emergency is a tough sell against a generator. As a solar installer, even though it's hard to sell an economic system, I like selling economic systems. There's kind of an expectation for these things to be economic, as opposed to like smart home stuff where it's just kind of fun. But as we learned, unless there's like mitigating circumstances, like you're doing an off-grid home and it costs tens of thousands of dollars to bring the power out to your property, it's going to be very hard to do battery power in an economic fashion. So if you liked what we had to say about the commercial side, yesterday, how that was so much more exciting because in the commercial industry, batteries can be economic. Here's kind of a peek into commercial design software capabilities. This is put out by a company called Energy Toolbase. And kind of like what we saw with the residential system where we're taking our energy in and energy out, but we were doing it very simplistically. We were taking our monthly consumption and dividing it into daily uses, and then taking our PV watts data, which I don't know if we ever did a PV watts calculation, but let's just do it real quick. Here's I'll put it in the chat box. Here's PV watts. Let's say let's do a PV watts calculation for Biloxi, Mississippi. And I'm not going to spend too much time on this. What I really want to show you is how quickly you can do a PV watts calculation. You just go to the website, you put in your address, and then I always like doing a 1 kilowatt system instead of a 4 kilowatt. It makes the math easy. You can play around with these parameters. Your performances won't change all that much. But here we're doing a system for a 1 kilowatt solar array in Biloxi, and we're getting our monthly production figures. And I'll just go down and download the hourly figures. That'll pop up in a minute. And so what I'm trying to illustrate right now is how you can build models like this in your own spreadsheets. But of course, what's nice, then we're going to go and show you what's nice. We're having some software intelligence behind it can take your design steps a little bit further. But anyway, this is our PV watts data. And so it's telling us for our zip code and for our 1 kilowatt solar array, we get the performance for every single month, every single day, every single hour, And at the end of the shoot, we get the power output of our solar array in AC wattages. And I'll often just, to make it something a little more useful, um, divide it by 1,000 to put it into kilowatts. And since I did it for a 1 kilowatt system, I'll also put in a little bit of a scalar. So I'll say, this will say, okay, I want to do it for a 8 kilowatt solar array. And so now by copying and pasting that cell, I now have my power output for an 8 kilowatt solar array for every hour of the day, for every day of the year. So here's, New Year's Eve at 11 a.m. at 11 p.m. The solar array's not doing anything because it's midnight, but we could see what the solar array was projected to do at noon on New Year's Eve. And for every hour of the day, for every day of the year, PV Watts will give you that solar production estimate. And so what Energy Toolbase does is it uses the exact same database as PV Watts. And so when you add a solar array to Energy Toolbase, that same production curve from the solar array will come from the same PV Watts data. Here Energy Toolbase is taking the same load profile data that we're actually, extracting locally in this smart home. But every commercial customer, because they're being billed by their peak kilowatt demand, if they're on a demand charge, then either in their online electrical account or by request from the power company, you can get this load profile data. And so what Energy Toolbase is doing is they're simulating an event where they're load leveling the building by this much power and charging the battery at night. And so they're showing the battery being charged, and then the battery being discharged, the battery being charged, and the battery being discharged. And where it comes down to on the tax credit is you only get the tax credit if you charge it with the batteries, with solar. So if you're doing grid charging with your batteries, you got to return the tax credit that you claimed on it. It's not, what they say is it's something like 80% of the battery has to be charged by renewables, and the percent difference that it's not charged by renewables, like if you charge it 96% renewables versus 4% grid, you actually have to return the 4% that you claimed for the tax credit but you didn't use. Anyway, what Energy Toolbase allows you to do is quickly run a couple of different simulations. So you could load level that amount, or you could load level that amount and see what that does to your battery bank size. At this point, I just do a lot of this stuff in my own Excel. But what I think is interesting about Energy Toolbase is they'll provide some optimization algorithms to help you hone in on what the ideal peak size is for you to demand manage and load level. As we go back to what we see in these slides is, the energy savings really aren't that important on a demand charge. I know it's kind of hard to see, but this is like, 100, or we're charging the battery, and so we're losing a few $100s by charging the battery. But that's not equivalent to the tens of thousands of dollars that we're saving total because of the demand management. So again, with demand management batteries, we're not worried about the energy cost at all because the demand savings are so much better. But what we can see through the Energy Toolbase algorithm is they're saying, okay, this is for a 29 kilowatt battery, a 57 kilowatt battery, an 86 kilowatt battery, 114, 143. what we see is the larger the battery gets, the dollar per kilowatt savings of the system, the cost, the return on investment for the system begins to decline the larger the battery gets. And that's why using commercial software is nice, is it can, you can, it's like hiring a mathematician to help you hone in on, your optimization problem instead of you doing it yourself. The reason for those diminishing returns, I'm just zooming in a bit. Let me get there. Is that, our loads are spiky, and the taller and steeper the load is versus something that is more steady and more like a plateau, shaving this spiky peak off it uses less battery power than what it would take to take the whole top off of this plateau. And so if we throttle back our battery, let's say we do a battery that's 1/3 the size of what's modeled. Instead of being able to load level down to here, we might only be able to load level down to here. But that narrower peak would be more cost effective to load level. In other words, the deeper you go with your load leveling, the wider your base load gets, to the point where you're having to load level base load, or your true base load, or your entire electric bill. Whereas if you just stay and focus on the peaks, your commercial peakers can get much more cost effective. So, it's a little bit of a chore, to show commercial peaker sizing. What I really do is put it into a visualization, and then I run a couple of different models and look at energy tool bases, where it's telling me to kind of dial in my array size. And even when it, gets me, okay, basically this is telling me I can do up to an 86 kilowatt system. And that might be out of, if this came from the same example, I know it's a little hard to see here, but this scale, this load in this example is about 160 kilowatts. So it's saying, once you do more than about half of your peak load, you start getting into diminishing returns. So I just think that that's interesting, that a smaller project can be more cost effective. So I think that that's a good starting point. Okay, so Phil said, what's the name of the website? It's called Energy Toolbase. And again, I try not to put too many like promotions of third-party software or anything in here, but they do give a free trial. And I talk about them in other classes because they make economic spreadsheets that are good enough quality to make a CFO smile. Let's see here. What are people saying? Hold on. Yeah, I think it's the best solar software out there, because it really just sticks to it'll do economic modeling. And so here we're, it's telling you, oh, we're using the PV Watts database. So this isn't stuff you can't do on your own. But then you're putting in the array size. They actually take a step further and are starting to program in spec sheets for the batteries. Let me just real quick cut over to, I think I had a little bit more clear images. So it'll model solar production, and this is really where when I'm trying to fine tune my solar model, it'll identify. You don't need to worry about, say, the weekdays or the weekends when no one's using the building. Um, but that might, if your goal is to not outflow anything onto the grid, that interval data will help you know what your maximum solar array might be. And then we kind of get into this more into detail in the commercial solar peaker class that basically goes into modeling this a little more in a little more advanced detail. But basically what we're doing here is this load profile is already a plateau. There's some spikes we could do, but not many. And so we're saying, well, look, when you add a solar array to the mix, it drags down that peak energy in the middle of the day. And then you get the batteries coming in and doing, the morning and evening load leveling. And so what you've done is you've taken the solar array that would normally be producing at, the dirt cheap energy rate that's near avoided cost on these larger facilities, 2 or 3 cents a kilowatt hour. The problem has always been, hey, solar produces during peak times, but we've never been able to get peak credit for it. And the solution is, come in and add a battery now, and you can all of a sudden start generating your peak energy and peak power demand. And with the right rate structure, which is a commercial rate structure, a demand-based rate structure, you can start, getting rewarded for that peak energy production without relying on the grid at all, without outflowing onto the grid or getting entangled into that grid policy. Although the reaction has been from grid rate makers is just to increase fixed fees, which, they're not going to let you get away as much as they can. And only because someone asked about it, let me see if I got any other energy tool-based pictures in here. No, I don't see any. Well, they do spreadsheet modeling as well. So let's see. Battery pricing is supposed to be dropping. I mean, it's Tesla is claiming that their cost of their battery is under $200 a kilowatt hour. And, I think we can kind of see that in backing out some of the pricing from the Tesla Powerwall and guessing what the retail price of their battery is to consumers. When I got into the solar industry in 2008, solar panels were $3.25 per watt. And now I'm buying solar panels for less than 50 cents per watt. So from 50 cents, from 350 to 50, we've seen a substantial decline in the price of the solar panel over the last 10 years. And that was because for the previous 10 years, there had been a huge push by manufacturers to ramp up the solar industry. It's not so much green energy policy that caused the solar revolution. It's really that the semiconductor manufacturers stopped experiencing exponential growth in computer chip manufacturing and needed another growth market for their silicon. So they started making a bunch of solar panels, and that meant more solar panels came to the market, and that led to a precipitous price drop in the cost of solar, the panels themselves falling more than 80% to the consumer over a 10-year period. So the question is, will batteries do the same? if you wait 10 years, will batteries be 80% cheaper than they are today? The answer is, and I don't know the answer to that. I would have thought that by now, because these are arguments people have been making for the last few years. I would have thought that the price drops by now would have been more evident. Um, I have to say from what so when I go and I get third party lithium iron phosphate pricing, it's always in the $700 a kilowatt hour range, and I find it hard to actually find low end lithium ion batteries available because they're still coming to market. It's hard to get access to a Tesla Powerwall, and it's actually kind of hard to get access to LG Chem batteries as well. I do have to say there seems to be an uptick in electric vehicle batteries, and whenever I get used, like when I'm pricing out batteries, just now I've started pricing out used lithium ion, and most of the dealers are like automotive dealers because they have access to direct electric vehicles. So I think I am today more encouraged just by recent used vehicle pricing in the kind of $130 a kilowatt hour range. So there still is I just feel like the price decline in lithium ion batteries is still yet to come. But I also feel like there are more used lithium ion batteries on the market than there ever have been. So that seems to be where like there's a lot of excitement in getting access to cheap lithium ion batteries that finally are giving lead acid the run of their money. Um, and in fact, I think that excitement is reflected in international building code, which allows these batteries to be used. And National Electric Code usually is a little bit further behind, more conservative, I guess. This is some solar information. I want to talk a little bit more about code issues. So I just kind of had some solar material and thought I'd throw in some things. I have never been more convinced about the reasons for load management than when you're doing batteries. There's really no difference in taking off load versus injecting power into it. And so so anyway, one things that I'm testing out like literally right now on this off-grid site is putting some intelligent smart plugs onto heavy continuous loads. Like it's a damp basement, and so we have a full-time dehumidifier. There's a couple of refrigerators here that are just for storing frozen food. That don't need to all be running when the air conditioners and things like that are clicking in. So unfortunately, the air conditioning company for this high-end heat pump, they've locked up their thermostat so that we don't have access to their thermostat for thermostat controls, and so that's making it kind of hard to do the temperature regulation we wanted. But anyway, you can see how if batteries do last a lot longer when not subject to their maximum discharge capabilities, then having some demand management, even if you're not on a demand rate schedule, can extend the life of the batteries and therefore make some economic sense. There are water heaters that are designed to work with solar so that the heating elements really only turn on with surplus solar production, or are better fine-tuned for that. So again, I just was bemoaning how here we have tank water heaters, and the idea was, we could just run them on low throughout the day, but because, the generic water heater tank manufacturer hasn't really given that much consideration, they just blow out the heating element full blown for, half an hour, and then the water tank just sits there for the rest of the day. So, definitely there's appliance selection is important when running your buildings off of batteries. And we're doing this, we're using a different technology, a wireless platform, but there's sensors that, just like an electrician's amp meter, go inside the service panel and monitor the amount of current that flows through it. We essentially install the same thing, and these systems go up to over 1,000 amps, so you can use them for monitoring industrial sites. Let's see. When picking out your battery inverters for commercial sites, you need to make sure that it's compatible with your particular facility, because sometimes it can be hard to find like a three-phase delta. Even sometimes the 208 three-phase battery inverters can be harder to find than the 480 volt. Let's see. These are just some code notes. Why do we not run lower voltage battery banks? Not only do you run into an amperage issue, but you also run into a voltage drop issue, where you will lose. What that means is once you get past circuits that need to be more than 20 or 40 feet long, you start needing, higher voltage systems just to pass the voltage a far enough distance that it'll still turn the appliance on at the end of the circuit. Now, all that concern we said about electric load, by and large, our service panels, like the 200 amp service panel versus the 400 amp service panel, are made by load calculations that are quite, overestimating the amount of electricity a home uses. Like it's pretty amazing that like homes are only using a few kilowatts of power unless the heavy duty appliances are on. But there's not much you can do about that. So this is kind of interesting on disconnect groupings. National Electric Code actually wants you to place your backup power disconnect switches in a separate location from your primary power disconnect switch. So that the idea being the fire department, they need to be able to quickly and readily shut the power down to your building. But while they're shutting the power down to your building, they don't want to accidentally turn off, an emergency power circuit that should not be powered down. Like, you could think about medical equipment, like a ventilator. You would still have a need for emergency circuits. So if you're backing up critical loads, and especially if you're using them to power, if you want emergency load circuits, just keep in mind that those should be physically spaced out from your other disconnects. And if that means your battery disconnect should be spaced separately from your solar disconnect, so be it. Let's see. Supply side connections. That's where you'll end up, supply side connections are difficult to avoid if you're trying to power the whole building with solar. And so, let's say I have a 200 amp service panel. So I'm just going to put a 200 amps. And then I'm coming in from my utility meter. Well, this conductor here is rated for 200 amps. And it's still on my side of the meter. And so often for large systems, for systems that are capable of supplying 200 amps, you're going to put them maybe even on their own, distribution panel or transfer switch or tap box or whatever it is. You're going to land them on between the meter and the service panel so that they can feed the full 200 amps into the house. You're allowed to put load management devices, surge arresters, and surge protected devices as a supply side connection. I think that this is kind of interesting because it sets up a situation where if you put a battery inverter here, and let's say this battery inverter is rated for 200 amps, and then you have your load that's rated for 200 amps, and then over here's your meter. Potentially, you could be pulling 200 amps of load and also charging 200 amps of batteries and smoking up that meter that's only rated for 200 amps. And so, in the past, we've been kind of assuming that supply side connections are going to be, like a solar array that's always going to be feeding and never going to be charging. And, so I wouldn't be surprised if an inspector, if you're doing a line side tap with a battery inverter, if they'll want to make sure that the battery is in kind of a zero export mode or a charge mode that ensures that it's not going to be charging when the home is otherwise pulling its full 200 amps. We talked about using a metal conduit in the battery rooms. So like flexible metal tubing. Let's see. And we're kind of at the end of our class. So these are just kind of some notes of things to look into in National Electric Code. Essentially you need a disconnect switch wherever it goes through a wall, wherever the battery cables go through a wall. So if you have the inverters on one side and the batteries on the other, you need a disconnect switch on both walls. I did notice that there's a question that's queued in wrong on the quiz, and that's my fault. I gave Andrew the wrong answer. But the question on the quiz is true or false. Can a battery sit on top of concrete? And the answer on the quiz is true, but the real answer is false. So that's the only one like that, but the answer is keyed in as true. But the problem is, and the reason why it's actually false, is that concrete can conduct electricity, and it can conduct electricity if it's wet. And, so, you might, I was just in a basement exterior battery wall chamber. I'm putting my hand up next to the concrete. I'm like, oh, this feels damp. It's on the other side of that concrete. It's an exterior concrete wall, and on the other side of the concrete is the drainage area for the house. And it's like, oh, well, if that water comes in through the concrete and saturates that concrete, it can conduct electricity. So You should always put your batteries, even if you're sitting them right down on the concrete, you should get a rubber mat and put them between the floor and the mat. And I guess before we go, the ventilation requirements for fire code for sealed batteries are different from the NEC versus the IFC. I mean, obviously the batteries need to be locked up, but that's more important because, you know, where those ring terminals lug onto the batteries, you know, they're not as well protected as other connections like solar wiring inside an inverter. And so, you know, your batteries need to be in a locked room or a locked box or a locked cabinet. Um, and then you know, just as a safety precaution. So, you know, sometimes I have clients that look at the battery bank and they look at the battery inverter and see the lugs and they're like, oh, is it dangerous if I touch that? It's like, well, you know, it is. It is. If you touch the hot to ground, or you know, have a metal tool that falls into the battery and touches two leads together, you know, bad things can happen. You know, whereas if you just stumble into a solar inverter, you know, there's less exposed stuff in a outdoor rated exterior mounted shell than there is in these control rooms with a lot of interconnected parts. So, you know, lock up your battery rooms.